Well, good morning, everybody. It's so nice to be here with you today. I've really enjoyed the talks that I got to see this morning. As I said, or as Annie nicely introduced, I'm going to talk about data harmonization and sharing in the nanoinformatics community specifically, and talk kind of in that about navigating convergence, which we all have heard the importance of and understand some of the challenges of. Within the incentive structures of research efforts, especially in a continually emerging field. So let me see, I have typically bad instincts about what button to push. Okay, so the first point I just want to make is why, as our repository that we're building and our set of tools at Saint is again called the Nanoinformatics Knowledge Commons. And so we're building it within the Center for the Environmental Implications of Nanotechnology, which is a 10-year NSF funded effort, but it's going to be ongoing. It's just that the NSF funding will end in its first iteration in the next couple years. So as we sunset our original kind of funding structure, we're of course doing what most centers like this do, and we're collaborating with a lot of different people, and a large number of our collaborators, project-wise, are in the European Union for a couple of reasons that are interesting actually in light of what we're talking about, barriers to collaboration. So in the EU, anything we do together with them, we're not competing with them, so we have more incentives to be just sort of wildly intellectually generous and share, because anything that we give to them is bonus for what they're being paid to work on and vice versa. So that's been nice. Also, the EU is investing heavily in nanoinformatics at a time when in the US it's less certain. I know there's plenty of different funding stories there that are similar in other fields. So this has been good. And in order to do this, we sort of used an old English kind of a concept of the commons, which is to say from the outset, philosophically, we're creating something where we want it to be shared, more than just open data, but really open and shared investment in curating data the exact same way so that we can all benefit from it. And so right now, the Nanoinformatics Knowledge Commons is started, or the NIC, as we call it. It has started within Saint, but because of the US-EU bridge, we also are including a lot of different data sets from other European projects, which are similarly large. So Saint is made up of 7 US universities and a number of international collaborators as well. And the same is the case for Nanophase, Serenade, iSaint, and the eNanoMapper project, which is a specifically ontology-based project. So all of these people we're hoping will kind of add their logos to the NIC, and then we can all claim it as something that we've all built. So we're trying to start out by following that philosophy of not rebuilding anything that's already been used and not needing to have our flag on the moon in order to have made progress. We want everybody to be able to put their flags. So one point to make in explaining kind of our approach and what we've done and what we specifically haven't done is to just make the point that in nano technology, we're early on. We don't have big data, really, although big data is a thing that many people say, and what we mean is, interoperable data sets where you learn more from your combined data than you could an individual study. But I think it's important for our procedures forward to say that, big data happens in fields like astronomy or in genomics, where you have a large number of data points for a limited number of established parameters. And maybe you even have established methods for generating those parameters, established metadata that are well understood protocols. Basically, you have assurances in place institutionally and in the maturity of the data set that allow you to know you can get to the point where it's findable, accessible, interoperable, reusable, all these things. So we have to be building the plane while we're flying it and so we don't have that situation yet in nanoinformatics. So the important thing here is not to throw up our hands and say, okay, well, we can't really play this game that you guys are playing in genomics for another 30 years. We have to figure out how do we focus as much or more on the processes and the flexible iterative updates so that we can do this modular approach that that was really well advocated in the previous session, but also be kind of building as we go to something that everyone can pay into. So we have broad data instead, and this means that we have a huge number of possible parameters. They are inconsistently measured parameters because we're still discovering what it is that you need to know about a nanomaterial to predict something that you would care about it doing. So all those things are emerging, and we have disparate data sets and disparate metadata, disparate methods. And so what we're going to talk about is kind of how we have grappled with that and tried to make some progress. So to say just kind of the things that we say were needed for nanoinformatics, in order to be, go into a field where there's just this infinite number of materials to span the whole periodic table and a bunch of variations on them and emerging everything, we have to make sure we have a compass so that we know, okay, what are we going to do that's going to make some progress? So we need to make sure that whatever solution we develop is going to serve the combined data and analytical needs of multiple sectors, multiple stakeholders. So we need to be able to support guidance that regulators are currently being asked to draft. We need to advance researchers' efforts, obviously, industry efforts. They're also trying to figure out where to put their energy in nanomaterials as well. So the kind of subpoints here are for a choir that is here already. So we understand that we need to combine and mine emerging data sets. We can't expect one person or one lab or even one field to crack these problems. And then to functionally make this happen across multiple parties, then a really important thing that we've realized partially through looking at others' progress over the past in, say, crystallography, astronomy, but partially through learning the hard way, is that it's really important to get the scale, the sequencing, the communication, and the incentives right. And so the reason I belabor that point here in explaining what we did is that we realized for us, with a mission-oriented research kind of agenda, that we had somewhat of a luxury that isn't shared by somebody who is specifically funded to create a universal library for nanomaterials, which has been attempted. We instead can say, if we gather the information that will help us elucidate the mechanisms that control nanomaterials in the environment and translate that information into helpful guidance for regulators, then we will have created a system that works. And so we said that we wouldn't be afraid to go small and specific to make progress that could then be generalizable and modularized. So I'm not sure modularized is a word, but you understand. So creating a various sharing practices that are kind of putting the responsibilities that you would have in a large scale IT project into a smaller scale research team with graduate students and postdocs and people that are going to need to move on. There are some challenges there. So developing the processes and practices helps us balance between having institutional memory and getting bogged down and only creating that without research progress. So with that in mind, we started to say, realistically, what can research projects deliver? We're going to have 3- and 4-year projects that we work sometimes in parallel and sometimes we baton pass. And so we need to have realistic expectations about what an individual project is going to add to. How much are they going to nod along and say, sure, we're going to use what you did, but then attempt to actually make their own mission-oriented flag and their own moon. And we need to be very open and sharing in our approach so that we can just be as transparent as possible, because we're really kind of linking this together with duct tape. Like ideally, a gigantic Google organization would come give us infinite funding for the infrastructure, right, to help this keep going. But as we all know in this room, that's not really going to come to pass. So how do we baton pass in a way that really passes the torch and doesn't lead to these droppages? So quickly, I won't talk about this too long, but just to explain why it's difficult, there is a necessity to grapple with the complexity of nanomaterial interactions that is somewhat different and apart from chemical databases and traditional toxicology. And it's because nanomaterials and their impacts depend very heavily on their surroundings. There's not so much of an equilibrium state. There are dynamic systems, there's kinetics involved. So you can't just say that, okay, this nanomaterial will impart this effect in this situation. Not to simplify and say you could do that for chemistry, but there are even more reasons that you can't do. So we need to say that we know the beaker doesn't equal the world. What is it about these environmental systems and the transformations, co-contaminants, changes that we we must capture if we're going to make sure that the effects we predict aren't possibly exactly wrong because we haven't included the right metadata. But in order to do that, because it's so hugely complex, without throwing up our hands or without kind of glossing over the details, we have to ask ourselves, why are we doing this in the first place? So we, at the top of this little cartoon, you see, okay, there's research papers, you know, field studies of varying complexity. We need to curate these and enter them into a repository. And we need to ask questions of this. So why are we doing it at all is to answer the research questions. That seems obvious, but it's been a really important compass for us to always remember. And to do that, we collect data, but we need to do that in a consistent format, consistent language to all this ontology work that we all understand already in repositories, the structure of which really matters for whether or not the data sets are later interoperable. And then we want to combine and query the data, and hopefully this is iterative, right? So if we create a critical mass, if we understand the metadata and can play with the relationships, then this should be able to allow us to pose new research questions, refine the methods that we are developing along the way to understand what even matters about nanomaterials, and then make sure that we just kind of create what we call premeditated interoperability, so that when you curate all the papers on nanotitanium dioxide, then you run a query on what happens in this scenario. You don't want to just get the one paper you did the experiments on that you haven't added to your knowledge base. And so that's also seems obvious, but it takes a lot of intentionality and focus around what it is we are going to gather the information on, to go small enough to make progress, to then be modularly generalizable. So the way we did this is to start small by asking our own research group across the 7 universities and our international collaborators and some external collaborators, what are your key research questions? So that if we built something that could let you ask those of our collective data and literature, then we would be adding value. And so what we came up with was, can key functional assays in a reference system predict exposure, biouptake, and toxicity? And so that I will spend some time in a couple slides talking more about what functional assays are. But many people in this room in toxicity already understand this concept. It was just kind of a new idea to bridge exposure scientists, material scientists, and toxicologists to say, sometimes when you don't know a mechanism, you might need to just describe a broader behavior and then say all of the conditions that were present when you observe that behavior, and then you can link it along to other outcomes. So we created the Nanoinformatics Knowledge Commons in a way that would allow us to capture enough detail about system dependency and transformations that we would be able to answer that question, whether or not these measurements we are proposing that everyone in nanotechnology take are predictive of things that we think they should be. And we've, this note on the side is just to say we've leveraged projects and programs wherever possible, with the idea that we don't want to make up a single term or word unless we have to. And so anytime we are referencing something, we really try to go out and we have some processes to use existing ontologies. So again, with this focus on shared methods, we want to make sure we stack the deck so that we are able to then ask questions that we care about. So we look at the nanomaterials and the environmental systems that we are doing experiments on, and then we are gathering these data about the functional assay methods. So can we, I guess there are some MAC issues, but can we look at that little triangle was an alpha, and that is attachment efficiency. So if we measure attachment efficiency in a lab in a consistent way of nanoparticles, we have the hypothesis that we would be able to both back out what were the environmental conditions and the materials properties ahead of it that led to that stickiness of the material, and then what does that alpha value say about what we might expect for it to go? Will it stay in soils? Is it gonna be taken up into a root? Of this type of thing. So somewhat of, if people are familiar of like a log KOW that would work in a chemistry situation. So we're stacking the deck in the NIC with these types of measurements, or dissolution rate, for example. This can let us predict things we care about. And then we're adding things that are very relevant for decision makers, like exposure pathway and what's the expected concentration and what's the method of release. So, so we can add these data as they go. This is just a little side note on functional assays, what they are. It's what we introduced, and we wrote a paper on this in 2015. Just saying to the field of nano EHS, if we use these intermediary semi-empirical parameters, it can help bridge the gap between the properties which we were trying to originally as a field link directly to the effects and the outcomes that we care about. The reason we have to use these is because the properties of the materials themselves turn out to be less of an indicator of what's going to happen than the surroundings that the materials are dropped into. So a complete material data set necessarily includes what some might have been thought of as metadata, but it's part of the definition of the material to talk about what medium it's in. And a lot of people understand this already from, say, a bioassay, but it wasn't as equally understood in fate and transport and in other fields that might just look at a material property and then the outcome, how critical it is to say, well, it could be because of these other things. So this is just an example from that paper that I won't belabor, but it shows, in fact, that if you have a higher attachment efficiency and a faster dissolution rate, you, in fact, do see a higher risk if you look at this across literature. So this isn't one specific study, but it's just showing the idea that if you can look at, okay, well, look at the same exact material in a different environment. One is sulfidized and one is a very little redox transformation, higher solubility state. Just because of the environment that the same material is in, you would have a higher or lower risk. And it's because the functional behavior of that material in that system. So because of this, this is a little map of everything that are in the Saint NIC. And so that includes the metadata, like bibliometrics, so you can back out who put this in there, who wrote it, all that. Analytical protocols. You know, in a more mature field, you might just have a standard link, and wherever that's the case, we have that. But sometimes we're developing it. And so, for example, there's still like three to even five kind of competing ways that people propose to measure attachment efficiency. So that's the example I'm pulling out. And so as those get updated, there has to be a process to say, okay, well, they used ICP-MS and they used it with these soils, and they made sure to measure this about those soils. So as those get updated, there has to be a human process of saying, okay, this is the information we need, and how can we know if we can compare across these? And that's just not going to get better and more standardized in time for us to develop a system that will give us the answers we need right now, which are, you know, do we let companies produce this? Do we recommend this? And so what I want to leave you with here in talking about our system is just we've had to be realistic about how some things are going to stay manual and they're going to stay really expensive in terms of person hours and intelligence and judgment. But if you build that in so that all the people on all the teams who are curating into this every week talk for, you know, an hour on Mondays across the world, then they can kind of update it. And that's just part of the expectations about how these linkages actually can get built. One other thing that's important about, so I showed you the content in the NIC database, but one thing that sets it apart and makes it so kind of labor intensive to curate into is that a thing that's extremely important with nanomaterials, again, is I'm saying this environmental dependency and also this temporal dependency. So if we have something called an instance, which we, again, to credit borrowing, we borrowed from the Nanomaterial Registry, started at our RTI and NIH. And they had this idea of an instance. We've kind of linked that to a specific point in time where if you measure a material, say, you know, silver powder as received from manufacturer, you measure some things about, they probably report some things about that powder. They probably don't report the medium that it was created in. So you would measure it, characterize it again. If we were going to ever put it into our system, we would only curate a study where they did do that, where they characterized also the medium in the as a second instance. And then you might have to treat that material before you are ready to do an analytical process. So if you're getting it ready for a TEM grid, or if you are going to get it ready to put into a mesocosm. So then you would measure the same things and you would name the instance. And then you would be able to back out when you're querying where along the process did this happen, and you can map the transformations. So the things you care about in the end, say if it's a surface affinity, may be different based on the different surroundings. So you've got to be able to look at those transformations. And then again, this is just to show that if you had multiple time points on a series, then you could include all of those, and they would be in the same record or story arc within the database. This would be overkill for some things that you don't need this for. If you just need to know a concentration and the material and then the LC50, then this is overkill. And we can put that kind of high level data in our system too, but we needed to build it to be able to track the transformations. Here is just a picture of why that's important. It's some data from Lavard, Hotze et al. In 2013 showing that sulfidation within a environmental system greatly decreases the toxicity. So if you were to not report the sulfidation that would happen to a material, you would get it completely wrong what would be expected to happen to the receptors in the system. This is just a picture that you were in no way intended to be able to read, but this shows an instance map. So I'm telling you that we have to capture each instance. Each blue box is an instance, and then the pink boxes below them are everything about the nanomaterial, and then the green and orange boxes above them are describing everything that's been measured about the material, the medium. So again, when we want to ask something, if it's going to be created at this level, then it's going to be, this would take about an 8-hour day for somebody to read that paper and then put it into the system. So why would researchers do that? Ever? I mean, we have no shortage of things eating up our time. And so we would do this obviously to get improved insight. And the only reason you would enter something over 8 hours into this laborious of a system is if you're going to be able to compare your data and combine it with others and then look at some trends. So this is just an example of our first app that we are sitting on top of the NIC. So our idea is that as critical mass grows, more and more people are going to be curating among our partnerships into this database, then we'll be able to ask more questions of it. But we also know that people who are going to be funding individual questions they want to ask, they need to have something that they can point to and say, this is a tool. So this is a tool that is funded by the Consumer Product Safety Commission and the Army Corps of Engineers. And it's called NanoFeat, which is the Nano Product Hazard and Exposure Assessment Tool. So on the right there, you see a dose response curve. It's showing that it's coming out of combined literature data on the left there of pristine nanomaterials. And then the user can put in a lot of different parameters, guessing about or using their estimates on exposure scenarios for a real product. And then by using a matrix factor that backs out how much of the material you would expect to see in the abraded stuff from a product and comparing that to the dose response curve, you can predict from a mixture of literature and expert judgment and exposure laboratory data what you might see as far as a response. So this is just the power of combining different types of data in the same repository. All I want you to get from this slide is that we are doing this pilot integration where we're asking these specific functional assay questions within SAINT, but we're also partnering heavily and doing the same thing with some projects, Nanophase that I mentioned and Serenade. So what that means is that all of our curators work together and they are using the exact same Excel format, exact same quality control through heavily trained. This is how we make the call of how to enter something into the NIC, and also heavy collaboration in creating a shared data dictionary. So we have used the term data dictionary as like a baby step to a true ontology. We just say, okay, we need to go low lift. You're flying through these papers or looking at your lab. Somebody maybe has done the work to create a whole ontology around the endpoint that you're interested in. So let's just have a shared Google Doc that we can all go to and say, when we are going to refer to TiO2, we type it this way. We don't have 55 different ways of doing it. And so we link to ontologies that are much more established, but we've decided to go pretty low tech to make it highly usable by the small core number of people. This is my last thing to say, which is just that we're building a research-based nanoinformatics knowledge commons is for the purpose, in our view, of serving risk assessment needs and modeling needs. And so to do this, we've kind of laid out here, and we'll share the slides, so it's not important that you need to read them all, but we've laid them here. You know, what do we have now? We have sort of these nascent data exchange formats that we've developed in our community. ISATAB Nano is a follow-on with ISATAB. We've got established curation templates. We've got established infrastructures like the NIC that you see here, established ontologies. And then we've got a pilot collaborative core of people who are willing to just say, here are my data, you can see them all. No one could possibly scoop something this complicated. We just need to help each other. And so just having that culture of that, I think, has been the most powerful. And so we're developing more and more automated processes, and hopefully developing more and more automated tools. But to be honest, that's kind of like the next VC level if you're thinking in startup terms. We're just very hyper-focused on making sure that we demonstrate utility through whatever kind of manual nitty-gritty way we need to do it. And we're more focused on saying, okay, these are the required data points. We're using all the tools that are out there, and we're going to work together to figure out what's important for next. So I'd like to just acknowledge everybody in St. Mark Wisner is the director, Greg Lowry is the deputy director, combined research effort of over 130 people, and then all of our generous EU collaborators who have been as open and sharing as we have tried to be ourselves. So thank you very much for your attention.